Two talks. The first talk is by Andrea Montanari, who has done some very interesting work on the intersection between statistical physics and communication. And today he'll talk to us about iterative algorithms. Thank you, David.
So David took care of interference problems. So this is joint work with David Dono and Arian Maleki. Arian is a student in Stanford graduating this year. Okay. So what is the talk about? Iterative algorithm is a large topic. A more detailed title could be asymptotic analysis of iterative algorithms on large random structures. So I'll try to describe some class of iterative algorithms and some methods to analyze them. But I won't be that general. In fact, I will focus on one specific problem that has been very fashionable over the last 3 to 4 years, that is under the name of compressed sensing. And the algorithms that I will describe are inspired by graphical models idea, by message passing ideas, but I will not discuss the connection because I will not have time. Okay, so let me be even more specific. One specific problem that I want to look at is the following. I have a signal S0 that is a high dimensional vector. And I measure it, I take linear measurements of this signal through a matrix A, and I observe it in some noise W. Okay? And my problem is to estimate S0 given the measurement Y and the measurement matrix A. Okay? So this is specific in quote unquote because practically there is no field in science or technology in which you don't face a problem that looks like this. Okay, and where the problem is, well, we know very little about how to solve this estimation problem when S0 has some structure. Okay, so it's simple in some way. Okay, and a very fashionable way of describing simplicity over the last few years has been to say, okay, S0 is perhaps sparse in a specific base. Okay, so as mostly 0 in some base. Yes.
Why it's not just this?
Good question. Yeah. In reality, for this talk, is not really important. It was important for the paper that we wrote, but we had also an S there. Okay, so S0, the not means the original one. Okay. Right. So when S0 is simple or structured, we don't have any good way of estimating it. That is any way that somehow is optimal with respect to mean square error and has low complexity. Okay? So what I try to convince you in this talk is that somehow a general theory of this problem is possible. Okay? And the caveat is that this is a statistical theory, that this doesn't work for any instance of this problem, but only in some average sense. And it works asymptotically. Okay? So this is the plan. I'll give you some background, then I'll describe this AMP algorithm, and then the application to compressed sensing, and time permitting, I'll describe the proof of the main theorem that I will quote, and this appears in these 3 papers in the archive. Okay? So the setting is again y is equal a S0 plus W0. S0 is a vector, n-dimensional. Y and W0 are n-dimensional vectors, and A is a matrix. Okay, so this is the figure. So is the notation clear? Okay. So let me just spend one word on normalization. Here I'm thinking of W as a vector for simplicity of IID normal 0 mean variance V random variables. So it's just white noise. And the asymptotic limit that I'm thinking of is big N and small n going to infinity with a fixed ratio, and the ratio I'll call delta. Okay? And for the sake of normalization, let me say that all the columns of this matrix A are normalized in such a way that their L2 norm is approximately 1. So they are approximately 1 over square root of n. Each entry is approximately 1 over square root of n. Okay? So there is one case of this problem that we actually know very well how to solve, and this is linear estimation. Okay? So let me discuss this briefly. In this case, I have the same problem, but the only information that I have about S naught is a constraint on its covariance. So its covariance is bounded by something. Okay. In this case, there is one, way of estimating it. One, kind of canonical way. I just hit A with A transpose, and then, I multiply it by A transpose A plus V minus 1 inverse. Why is this a good estimator? There is a number of justifications for it. One justification is that this is minimax optimal. So what does this mean? That is the one that achieves the minimal.
Missing an identity matrix.
Okay, so here V is V times identity. Any questions? Okay. So its minimax optimal means that achieves the smallest mean square error over all distributions of the input that satisfy this constraint. Okay. So it's the best of the worst case. Okay. So another nice feature of this estimator is that it's very easy to implement. You have just to invert a square matrix. Okay.
So what's the statistics on W naught?
Is normal 0 V. Okay.
Okay.
So it's IID, normal Z.
VI. Covariance VI.
See, V, let's say that they are all equal, the covariance. Okay, so you have just to invert a matrix, but, okay, for the sake of, the argument, let me say that I don't know how to invert matrices. I mean, I didn't take linear algebra. So I'll do the following. I can come up with an iterative scheme. So what I want to solve is this linear system for x. Okay? This gives me the estimator. So let me add to both sides x, first of all, and pass A transpose A on the other side. One good reason for doing this is that here the diagonal entries of this matrix are 1 by the normalization condition. So by subtracting 1 here, I made this matrix smaller in some sense. And now I can interpret this as an iterative algorithm. Right? I just divide by 1 plus V, and I get another equation, and then I can iterate this equation. So the algorithm looks like this. At each time step, I have an estimate. I subtract its contribution to the measurements. I hit with A transpose, and I add it to the current estimate. Okay? This gives me somehow a noisy estimate of my vector S naught. And then I shrink it by a factor 1 over 1 plus V. So I want to think of this fact, the fact that I'm shrinking this, I'm multiplying by this coefficient, as just, I try to estimate, I'm trying to applying a scalar estimator. If you think of it, this is the scalar case of this general estimator, right? So the interpretation of this iterative algorithm is that I do matched filter, which is a very common case, and then I do scalar estimation at each step. Okay. Something looks weird here, and what is weird is that here what should enter in this position is the variance of this object, while what appears in my derivation is the variance of the noise. So this is not quite the same. This will play, will be clearer a little bit in a while. Okay, so there is one other case that we know how to do, and this is the scalar case. Okay, the nonlinear scalar case. So let me take an example. Here, the dimensions are 1. Small n is equal to big N is equal to 1. And so I observe S naught plus W naught, where W naught is Gaussian. And now I want some constraint of S naught that makes the problem nonlinear. So a very popular constraint nowadays is to say that S naught is sparse. So what does it mean for a random variable to be sparse? It means that the probability that is different from 0 is at most epsilon. Luckily, also in this case, there is one canonical way of estimating it, okay, in some sense. And this is the following. If the observation is smaller in absolute value than theta, a threshold, I'll say 0. This is just noise. Okay? If it is larger than a threshold, if it is bigger than theta, I subtract theta. If it is smaller, I add theta. Okay? And this is the same justification as before. That is, this is minimax optimal. If you choose in the right way the threshold, if you choose theta to be some function of epsilon, that is highly non-trivial function times v, this is minimax optimal over the class of signals that have this constraint. Okay? So this achieves the smallest mean square error over the worst case input distribution. Okay? And tau of epsilon has to be tuned in the right way. Right? And if you have never seen this function, this is what is called the soft threshold function that I described before. Okay, so now to the real problem of today. And let me describe this algorithm. So now the real problem that you want to say is S naught. We have some constraint on S naught. We want to observe A S naught plus W naught. And here everything is high dimensional vectors. So it's a difficult problem. And the source is sparse, meaning the probability that each entry is different from 0 is at most epsilon. Okay? So at this point, you might think that everything that we've done for linear estimation we can throw out over the window, right? Because the problem is just nonlinear. Right? But remember, this naive iterative algorithm we came up with. Okay? This was matched filter plus scalar estimation. Right? This was my interpretation of it. Now, if I interpret this as a scalar estimation, there is a very natural generalization. That is, I just replace this by the scalar estimation, the scalar estimator that is suited to the sparse source.
That's a condition on marginals only that you have? The notion of sparsity can be argued with, right?
So, yeah, okay, so this is a model. It's just for justifying an algorithm, right? So here the condition that I'm posing, let's say it's just for marginals.
But will that be an analog of the Donahoe-Johnston theorem?
No. I mean, okay, hopefully in a few years, let's say. Okay, so this is a naive way of doing it. At each time what I do this matched filter kind of operation, and then I do soft thresholding. And I give myself the freedom of let the thresholds at each iteration change possibly. Okay, yeah.
So for the linear case with the covariance constraint on the input, the linear estimator is optimal for Gaussian input, right?
Right.
So not only is it minimax optimal, it's optimal
Right.
conditional expectation for a particular distribution.
Right.
Is there an analogous thing for?
Yeah. So this is the min-max distribution. I mean, the worst case distribution is the 3-point distribution. So it's a distribution that has a point mass of plus a point mass on 0, and a point mass on minus a. And the weight of the three masses depend on epsilon to make the worst case. Okay, so I didn't come up with this algorithm. This algorithm is in fact very well known, and there are at least 10 papers on it. It's called iterative soft thresholding. It's very simple. It has a problem, and the problem is that there is no reason why it should work, right? Because we just came up, we just invented it as an heuristic, really.
What
right?
is it? Is any function? No, that's
Eta is this soft thresholding.
And it's coordinate wise.
Theta of t for the moment I'm saying is a sequence of real numbers, and a priori I don't know how really to set them. It's reasonable to set them as the same order as the variance of this object, but these 10 or 20 papers of iterative sets of thresholding don't give any canonical way of fixing them, just some hand-waving rules. Okay. So somehow the point of the talk is that surprisingly there is some very interesting evidence that this algorithm works, And this algorithm is identical to the one before, except for this single term. Right? So here what I'm doing is that I'm taking the vector z at time t minus 1 and multiplying it by a sequence of scalar b's. Okay, bt. This is what we call approximate message passing, right, for reasons that I will not explain. And here the sequence of numbers b is not arbitrary, but is given by this formula. So, okay, let me not parse the formula. It's very easy. I mean, it takes 1 minute. You know, what is important to see is that the formula is as easy or as difficult to compute, to evaluate, as you know the expressions that we have here. So there is essentially, once you implement iterative soft thresholding, there is no, or essentially no overhead in implementing this one.
What is eta prime?
The derivative of eta with respect to the first argument. So it's essentially, it's, you know, if you remember, okay, this is more general of this eta, but is 1 if the argument is bigger than the threshold in absolute value, and 0 otherwise.
Normalized by little m, not capital.
Yeah. This is what, I mean, it's not arbitrary. This is, okay.
Delta.
Yeah. So there is a factor 1 over there.
Yeah.
Just to clarify, the eta is operated on a component-wise basis.
Yeah.
Right?
So
Because you operate on a vector.
good question. So here eta is a scalar function. When I apply it to a vector, what I mean is that I apply it component by component. Okay, so now I'll try to describe the evidence why this works. Okay, so you might say, what is the big deal with this term? Okay, so this term is, we call Onsager term for historical reason, comes from physics, the motivation. And here is a small simulation that I did actually on the plane going to Cairo. So it's a very small simulation. So what I did is that I implemented the algorithm, and then I look at this object, xt plus atzt. So this is really the argument of eta. Okay? I look at the component I. Let's say I was equal to 17. The component I was such that the signal was equal to 1 on that component. So the actual signal is 1 on that component. And look at my current noisy estimate. Okay? And now I repeated, you know, probably 100 times I ran the algorithm for 4 iterations. Okay? Each time with a new sensing matrix, with a new measurement matrix. And then I plotted the histogram of this estimate. Okay? So this is the histogram without this Onsager term. This is the red line is the histogram, and this is the histogram with the Onsager term. Okay? And on top of it, I plotted the best Gaussian fit. Okay? This is the blue line. So I say, Venkat, what is the difference between these two?
Closer to the best Gaussian fit.
Okay, so this is, Venkat is a statistician. So this is, you know, really is, you know, it would be hard to tell it apart from a Gaussian. While this is clearly not Gaussian, you know, you see by eye, you can check it more, you know, closely, etc. And plus this is, you know, this vertical line is the mean of the Gaussian. In this case, it's 1. In this case, it's 0.75 something.
Excuse me, your noise is still Gaussian?
Sorry?
The noise is
Noise is still Gaussian. Okay? But the algorithm is non-linear, right?
Right.
So there is no reason why this stuff should be Gaussian. Okay? No, not reason a priori, no simple reason.
And why do you compute the distribution of x plus a z and not just x?
Well, you know, if this is Gaussian, here I'm applying a nonlinear function, so the result will not be Gaussian, right? So now why it's important, I mean, why you care about this object being a Gaussian? Because thinking of what eta is doing optimal scalar estimation in Gaussian noise. Okay? So if the argument remains Gaussian, the function that they are using is optimal at each step. The nonlinear estimation is going to work optimally at each step. If the object here is not Gaussian, then the eta function is not going to work well, right? Okay, so this is somehow the magic. This is a simulation, so you might wonder, is this true or it's just, no, Venkat was wrong and it's not really Gaussian. Okay, so we have a theorem that actually we are submitting to SAT with Moss and Bayati, and this is for a specific case, the case in which the coefficients are themselves IAD Gaussians. Okay? Notice that even in this case there is no reason a priori for this object to be Gaussian because the whole thing is nonlinear. Right? But this is the theorem, so take the matrix to be normal 0, 1 over n, and look at the empirical law of this object. So this is this object that I was plotting minus the signal. So these are endpoints. You look at the empirical law. This converges weakly to a normal, 0 tau, almost surely as n goes to infinity.
So this has some flavor of partially observed dynamic programming for control, right? I mean, you might think that you're observing the watered down version of the observation through the eta somehow. And then you're trying to have some kind of a state that is talking about the distribution of what the true observation is given what you're working with. Does that explain the Onzaga term? It has flavor of that.
I don't know, really. I mean, one reason why I'm giving this talk because I would be very happy to hear if things like that, phenomena like that appear in other fields. Okay? Okay, so this is Gaussian. Not only that is true, but you can compute the variances, and the variances are given by this recursion. So what is this recursion? This is just the scalar recursion that you would obtain if each time there was new fresh noise. So you see here you have x naught is your original signal. You add the Gaussian with the variance tau square, and then you apply the scalar, and then you subtract the signal, and then you compute the second moment of this. This gives you the variance at the next step. So there is a simple functional recursion that gives you the variances, step by step.
Excuse me, just another question.
Yeah.
The function eta depends on the threshold, right? I mean, there's a theta
Right.
parameter. So your result is independent of the theta.
Right. This theorem works for any theta. Instead, it works for any function eta, sequence of functions that are Lipschitz continuous. Okay? But I just mentioned it for this. And one thing that is interesting about these results is that it gives a way to actually determine what are the optimal theta, okay? Because you simply find at each time the theta that minimizes this object. Okay? So now, thanks to this state, so we call this a state evolution. Thanks to this, there is no free parameter anymore in the algorithm, something that was not true for iterative soft thresholding. Okay, so this was for a specific ensemble of matrices. This is normal 0, 1 over n. One might wonder what happens if you look at other matrices. Okay, so we went on and on doing all sorts of simulation to check this phenomenon. This is very close to Gaussian. This is you take a matrix and you take each column to be independent and uniformly random on the unit sphere. Okay. Take the unit sphere in n dimension, and then you take n columns like that. And what I'm plotting here is essentially the same object as before. I take the empirical distribution, I take the quantiles of the empirical distribution, and I plot it against the quantiles of the normal. Okay? So a straight lines means that this is a normal distribution. And here is, there is a red line below that is the best linear fit. And as you see, you cannot see the red line, meaning that this is really very well Gaussian. And the fact that it's getting horizontal means that the variance is reducing at each step. Okay. So this was a matrix. The uniform distribution over the sphere is in reality, we know, very close to the Gaussian distribution in a number of ways. This is a very different distribution. here I'm taking the matrix A. This is a almost realistic sensing matrix. I take the Fourier matrix n by n. Okay. So the matrix of e to the j 2 pi I k over n square root of minus 1
Right, just to ask.
k. I don't know. I'm a physicist as background, so we use I for square root of minus 1. Engineers use j.
But now in electrical engineering department. So I see that you switched to J.
I know. I'm completely confused. So now I take this matrix and just I take a random subset of its rows, okay? Uniformly at random. So I sample rows from this square matrix. So this is like picking your measurements are random Fourier coefficients, okay? So this gives me, so each measurement is r I times naught is a random Fourier coefficient. So this is a completely non-Gaussian distribution, and I plot the same thing, okay? For my algorithm, for our algorithm, I plot the quantiles of, these estimates versus the quantiles of the normals, and again, it's different. It's very difficult to tell it apart from a linear, right? From the ensemble. It's again very linear. This is still another, numerical check. Here, what we plot is, again, the prediction of this state evolution formula versus, for instance, the mean square error. So here, after 10 iteration, I compute the mean square error produced by the algorithm. The mean square error, as can be predicted through this state evolution formula. So the state evolution formula allows to predict all sorts of quantities. One is this. Here I plot a mean square error on 0 element. This is the misdetection rate. That is the one elements of the vector that you detect as zeros. This is the false alarm rate. Okay. Notice that the scale is very blown up. So all of that, those match. Here, each plot there are two curves. One curve is blue and the other curve is red. One is the empirical result, the other is the theoretical prediction, and again, you cannot see two curves because they are very close to each other.
So the only source of randomness is the coordinates of the noise, right? So there ought to be some linear functional that describes what this object is.
So,
Or approximately linear description in terms of the noise coordinates.
well, there are,
A is
okay,
random.
so A is random, the
A
measurement
is
matrix
random also,
is,
okay.
so in any given experiment, A is given, right? But the theorem is about a random matrix. Right? So it should hold, for instance, it holds with high probability for any given random matrix, right?
I guess the question was whether there's some structure to the correlation with the underlying noise.
Yeah.
Everything inside is Gaussian, right?
Well, but okay, the noise is not really crucial because here, for instance, I'm plotting the results without noise. Okay, so you can do linear estimation without noise, and here this is what I'm doing. I mean, you can do estimation without noise.
When you say random, do you mean any particular kind of random?
Okay, so the theorem is about IID normal entries, right? But so I showed you a series of examples in which, for instance, this works for random Fourier matrices, okay? Section of the Fourier matrix.
So when you say universality, this is universality analogous to, say, eigenvalue distribution of large random matrices.
Yeah, this is a good
Universal.
example. Yeah, I mean, ideally, okay, so we proved one theorem for the Gaussian. Ideally, one would like to prove it, for instance, it should be true that it's all for any matrix with IID entries, variance 1 over n, and bounded fourth moment, for instance, okay? So this I listed as an open problem in the session today. I have no clue how to prove it. Okay. And that would be very interesting, of course, in knowing. So in the second half of the talk, let me talk about application to this compressed sensing story. So what is compressed sensing? So probably many of you have heard it, the name many times. To those who haven't, compressed sensing is exactly the same thing as before, except that now I'm taking the matrix A to be very fat. Okay? And the idea here is that the selling point is that if the signal is highly structured, you might need far fewer measurements than dimensions to actually reconstruct the signal from Y. Okay? So even if you take few measurements of a sparse signal, you can reconstruct the sparse signal. So I will not give any bibliography on this. There have been probably more than 1,000 papers over the last 4 years. There is probably one paper a day on this topic. More than okay, to simplify things, I'll focus on the noiseless case. So this W naught from here on is 0. Okay, it's still a highly non-trivial problem. Why? Because you are observing less dimension than in the inputs. Okay, and in this story there is one kind of golden standard, one canonical way to, one way that a lot of people have studied to reconstruct the signal, and this is called the basis pursuit, or has many names, but the idea is just you minimize the L1 norm of x subject to the constraint y is equal to ax. Okay, so there are, the basic justification for this is that this should be some kind of proxy, convex proxy for sparsity. Okay, you want to ideally you want to minimize the sparsity and minimize the number of non-zero entries, but the number of non-zero entries of a vector is a horrible function. It is non-convex, so you minimize the L1 norm.
Yes, that's right. What is given?
Any question?
Why is given?
Yeah. So
Why is given?
the problem is exactly as before. Y is given, A is given, and you want to reconstruct S naught.
Right.
Is that okay? And the reason why it's not trivial is that it's underdetermined. Okay? So this thing works, this L1 minimization works. There is a number of reasons that people have invented to explain why it works. One that is very interesting is this phase transition phenomenon. So let me explain what this is. Okay, so this is an explanation for this L0, L1 equivalence. So here again, I'm looking at a system that is getting larger and larger with the aspect ratio of this matrix fixed. The aspect ratio is delta, and is the amount of undersampling. Let's say that the probability that S naught I is different from 0, I'll call it delta rho. Okay? In other words, rho is the ratio between the number of measurements that I'm taking and the number of non-zero entries in the vector. Okay? So the following happens. So the two variables are between 0 and 1. The following happens at large delta means that so in this plot there is a large row. I'm taking a lot of measurements. A large row, there are lots of degrees of freedom. So what happens is that the L1 reconstruction fails. A small row, there are few degrees of freedom. The vector is very sparse, and the L1 reconstruction works. And the phenomenon is not smooth, but there is a line in this plane, such that below this line, this algorithm, this convex optimization works with high probability, and above this line, it doesn't work with high probability. Yes.
The line the non-inclusive.
Sorry?
The line the non-inclusive.
There?
Is there an expression for that? Like?
Good question. Well, one slide. Because I heard that in a talk, a good question is just an euphemism for saying I have the answer in the next slide.
Very good question for a speaker.
So delta and delta rho seems to be two separate parameters. Why do you decide to parameterize it this way?
Calling this delta rho?
Yeah.
Okay, so you could call this rho itself. So this is, the way of normalizing things of David Dono. And the rationale for this is that rho really measures, the number of degrees of freedom per measurement. Okay? because delta is the number of measurements. So you don't have to measure the number of degrees of freedom per dimension, but the number of degrees of freedom that is non-zero entries per measurements.
So there is no chance if probability is bigger than delta, yeah?
Sorry?
So there is no chance that to reconstruct
Right.
that a particular probability is bigger than delta.
Right. You need at least as many measurements. Of course, you need at least as many measurements as non-zero entry in the matrix. This is what you would need if you knew which one are the non-zero entries. In fact, you need a bit more because you need to know,
And
figure out.
it shows how much more.
Yeah, this shows exactly how much more. The amount, this is below 1. So if this line is high, this is good. This line is low, it means bad. Okay. So there is an expression for this line, and this is was computed by Dono and Tanner, and it's based on this equivalence with convex with random polytope geometry. And the equivalence is the following. I will not explain why it works, but L1 minimization works if and only if the following is true. This polytope, I'll tell you this is a random polytope, I'll tell you in a minute which polytope is this, is outwardly k-neighborly. Okay? Okay, S0 and k is the sparsity of S0. Okay? The number of non-zero entry of S0 here. Okay? So let me tell you what is this polytope. You take, essentially you take the positive orthant in n dimension, you intersect it with the plane with all that corresponds to the sum of all coordinates equal 1. This gives you, the standard simplex. Okay? And now I apply the matrix A. So you take, this is a polytope in high dimension. A gives you a random projection in low dimension. Now you get a polytope in small n dimension. Okay? K neighborly means the following. If you look at any 3 vertices, 3 neighborly, any k vertices, you look at the polytope, the convex hull of these k vertices, this is a face of the polytope. Okay? For instance, if you have, so this is, so this is, for instance, 2 neighborly. No, it's not 2 neighborly, because if I take any 2 vertices, there are couples of 2 vertices that are a face, but these 2 are not a face. On the other hand, this is 2 neighborly, because if I take 2 vertices, these are formally a face, always a face.
Is there an entropic characterization of that curve?
Good question.
Okay, so this is an excellent question. Okay, I don't have. Okay, so
You don't have an answer, it's
That's not
excellent.
a good question.
so now once you have this equivalence, the point of determining this curve is the following. You take such a random polytope, and you ask what is the probability that if I take 100 vertices, the convex hull of these 100 vertices is a face. Yeah? Luckily enough, somebody has computed this probability, at least. And this somebody is Bershik and Sporschier. So thanks to this, you can get this curve. And it's a very long formula. In fact, there is a paper by David Dono and Jared Tanner. It's a 6 pages paper, and 5 pages just taken by giving the formulas. So there is an expression, but I was never able to parse it. Okay?
So sorry, going back to the threshold result, the picture. So this result is with respect to the random matrix. What's the ensemble on the random matrix?
So here the ensemble, I think it's any rotational invariant ensemble.
Any rotation. So this is a universal result.
Well, it's less universal
Than you want.
for instance, a random signs doesn't work.
Or doesn't work.
Right, because random sign is not a rotational invariant, right?
It doesn't work as in this result doesn't hold, or does it?
This result, the result holds, empirically holds, but the proof doesn't. Because you see, what you want is that essentially this polytope has to be a corresponds to take a random rotation of the simplex and project it, or correspond to project it on a uniformly random plane or low dimensional space. Okay, so at this point, one thing that you want to do, okay, now you know what L1 does, what are the performances of L1. In a precise sense, these are given by this curve in this delta rho plane. What does this AMP, very naive iterative algorithm does? So these are, okay, the stars are the AMP threshold determined empirically, and the curve is the random geometry result. So they are on top of each other. Okay. So we didn't check this just for this problem, but for two more problems. You can look at generalizations of this compressed sensing problem. This is a generalization in which all the coefficients of the signal are non-negative. You get a slightly better curve because you have more information, so fewer measurements are required.
Oh, you mean the entries of A?
Oh, no, all the entries of S naught.
Oh, S naught. Prior information. You have more prior information.
Yeah, you have more prior information. In this case, instead, the purple line corresponds to saying, I don't know anything about the sparsity, but all the entries of S naught are between +1 and -1, and some fraction of it are actually equal to +1 and -1, and delta tells you what is the fraction that is equal to +1 and -1. So this corresponds to three different, somehow geometric problem. For instance, this corresponds to the signal being in a high-dimensional cube. Okay, and for all of the three problems, the AMP algorithm, or a variation of the AMP algorithm, recovers exactly the L1 phase transition. One byproduct of this, by the way, is that the AMP algorithm, I can compute the threshold now using the state evolution formalism. Right? So the state evolution that I described before, this evolution of the variance, gives me a way to compute the threshold of AMP. Okay? So this gives a completely alternative way of computing this phase transition for random polytope geometry. Okay? And the interesting fact is that now we have a closed form expression thanks to this.
So I'm confused. The dotted line, the stars are what you can compute using the state evolution, yeah?
No, the dots are just simulations.
Or just simulations?
So we take a genuine sparse signal, we apply a matrix, and we run our algorithm, and this point is where the success probability crosses 50%. This you can also compute from the state evolution and obtain exactly the same curve as normal.
And you prove that that curve that you can compute is the same as the curve for L1?
Okay, so this is a good question, but I don't have the answer. I don't have the answer on the slides.
Because you said there was no closed form expression for the other one.
Yeah, that's true. So this is another open problem. Okay, so as I told you, the Dono expression is 4 pages. Our expression, the expression from state evolution is 2 lines. Okay, so there is a very messy calculus problem that is checking that these two are the same thing. Okay, this will take probably 1 year of a PhD or several months of a PhD student, right? And what we did is that I didn't have several months to do this. So what we did is that we just computed both numerically, and they coincide to 10 digits, right? So they are the same. But it's amazing. Okay, I can show you.
You don't have a formal proof, right?
No, I don't have a formal proof.
You can plug it into Mathematica or something and
To become 100 pages.
Yeah, I mean, no, it's not that easy because Dono formula, there is a series of optimization over several parameters. It's like, for you, Gallagher formula for the error exponents, but many more parameters, right? So I can, okay, I don't have it here.
it's okay, we can do it offline.
Okay. So one other thing, so at this point you can also check universality with respect to various features. This is universality with respect to the signal distribution for 3 different distribution of the non-zero entries, uniform random signs, random Gaussian, Cauchy distribution, and they coincide very precisely. This is universality with respect to the matrix. This is the uniformly standard ensemble. This is IID columns with the unit norm, the sphere, the Fourier ensemble, random section of the Fourier matrix, and the Rademacher ensemble, that is random IID signs. And again, it's very difficult to say the difference. Really, the very surprising one is the Fourier, because the Fourier is really, yeah.
When you say universality, the way I understand it, if you mean it here, it's not universality with everything, there are constraints.
Yeah.
So what are the constraints? For instance, the distribution of the signal is headed for what distributions? Exponential family or non-exponential?
We had for instance, there is Cauchy there, so it's power law. One thing that for instance makes this change if you take the matrix measurement matrix very sparse itself. Okay, so you can take the measurement matrix that is the adjacency graph of a bounded degree expander. Then things become pretty different, right? But as soon as the entries are roughly of the same order, and there is not too much correlation, it works. Now, precisely telling
the matrix is particularly interesting because it may have geometric meaning. So, do you need rotation invariance? You don't need rotation invariance?
No, it doesn't seem that we have rotation. We need rotation invariance. I mean, I'm sure, for instance, that it's sufficient to have all the second moments equal and the bounded fourth moment. This I'm sure. I don't know how to prove it, but this has not the rotation invariance, right? For instance, random size, random plus minus ones. Okay, so this I'm sure. Okay. This is comparison with a number of other algorithms. Okay. Perhaps I'll pass to a sketch of the proof of this main theorem in the last 10 minutes. It's just 2 slides, just to tell what is the basic idea. And for telling you the idea of the proof, I'll just describe a slightly simpler setting. The setting is the following. I take an n by n matrix, so just a square matrix, IID entries, but now the matrix is symmetric. Okay? So from a bipartite case with a non-symmetric matrix, I'm passing to a symmetric case. Okay? And each entry is normal 0, 1 over n, and on the diagonal, say 0. Okay? And in this case, the algorithm that I want to analyze the following. The first, you have a vector, n-dimensional. The first value is 0. And at each time, I update it in the following way. The new value is the matrix applies to f x of t. Okay. This will be without the Onsager term. And now I add this Onsager term. Okay. This is how the Onsager term for some choice of the B's. Okay. The B's is a deterministic sequence that if you want, if I'm good, I can fix at the end of the day. Okay, there is a prescription, but I'll not write it. And here the function is applied component-wise, and say it's Lipschitz or differentiable. Yeah. Sorry? T is discrete, so I'm updating all the vectors simultaneously. Okay, now I want to compute the distribution of one coordinate of x and show that it's asymptotically Gaussian. Okay, so this is, okay, we tried for a while to do this, and then actually the idea came because I heard a talk by Erwin Bolthausen in a probability workshop, and so this is a good example of interaction between probability and, say, optimization, and he was solving a very closely related problem, and this is this conditioning trick. So let me write mt for f of xt. Okay. And call st the sigma algebra generated by x0, x1 up to xt. Okay. Therefore, the sigma algebra in particular contains also the m's. Now I want to compute the distribution of x at the next, or approximate the distribution of x at the next iteration. Okay. What is the big trouble? At the first iteration, this is very easy because x0 is just a deterministic vector. At next iteration, this becomes different because the matrix A is correlated with the sigma algebra sigma t. In particular, is correlated with MT. So A is correlated with this object. So what is the idea that a posteriori is very simple is that is there a question?
No, it's sigma and the Gothic letter above are the same.
So this
And the sigma t downstairs.
sorry.
Okay.
Yeah, typo. So this is should be the Gothic sigma. Okay, so what is the idea? So A and M are correlated. At this point, I could just stop and give up. But the nice idea is to compute the conditional distribution of A given this sigma algebra. Okay. Okay. This might seem very difficult, but think of the following: what does it mean observing the sigma algebra sigma t? As far as A is concerned, means observing the following. Okay, this should be B. I'm sorry. Okay, so this should be bt minus 1. So it corresponds observing a series of linear conditions of the form xt plus something, this is the Onsager terms, equal A times mt minus 1. Right? What I'm really observing, look at this equation, this equal to this. I observe m, I observe mt minus 1. Let's say that I'm observing, or observe mt minus 1, I observe mt minus 2, and observe xt. This means that I'm observing this linear equation for A. So what
BT doesn't depend on A?
Sorry?
BT
doesn't, it's a deterministic sequence. Okay? So what I'm really observing is a series of linear conditions. It's this kind of event. Therefore, what the conditional distribution is just a conditional distribution of a random variable given linear observation. And this random variable at this point, I said that is Gaussian. So its conditional distribution is the conditional expectation. So it's equal distribution to the conditional expectation plus linear projection, a projection of an independent Gaussian, where now this A nu is independent of sigma t. I'm just using the fact that, okay, for a Gaussian random variable, the conditional distribution given linear observation is equal to conditional expectation plus projection of an independent. Okay, so at this point, what I want to analyze is this iteration. Yeah. Okay, so this in distribution, I can replace this with this object. So I obtain a new Gaussian matrix times the current vector plus a conditional expectation that I call EMT minus the Onsager term. Okay. Here, okay, this projection in reality doesn't really matter. You can neglect it because it's a high-dimensional projector. So this is equal to the new random matrix times the orthogonal M plus something that is measurable on this sigma algebra, something that is just a function of the past state. Okay. So at this point, you have really to carefully compute this object, and you can show that what happens is that these terms exactly kills all non-Gaussian terms here. This term is non-Gaussian because M is a nonlinear function of X. Okay, but what happens if you keep track of all non-Gaussian terms here, you see that this minus BT is exactly what kills them.
Why you chose the BT in the first place?
Sorry?
How you chose the BT?
Yeah, this is, if you want, one way of choosing the BT. Once you arrive at this term, you compute this very carefully, you show that asymptotically unknown Gaussian terms are proportional to mt minus 1, and you put the Onsager, the coefficient to be exactly the one that kills that coefficient.
So A nu has the same distribution as the original distribution?
Yeah. So this is essentially telling you that, thanks to, something that you would like to do when you see this, when you see this linear, this dynamics, what you would like to do is use a new fresh matrix at each iteration. Okay? Without this object, if you want to analyze this without these Onsager terms, you would like to sample a new fresh matrix at each iteration. Okay? That is very easy to analyze. Unhappily, it's wrong. Now, the point is that if I add this term, this becomes true. Okay? This naive calculation becomes true. Okay. So as a brief conclusion, let me tell you what I didn't talk about. I did not say anything about where these magic terms comes from. I told you more or less how to prove that it works, but know how to invent it. There is a, related to this, there is an interesting relation that I didn't mention with message passing algorithm, like they are using in coding and with density evolution. That it's very well used in coding theory. This algorithm is very close to a number of convex optimization algorithms, for instance, Bregman iteration, but is different from all of them. I don't know really what is the connection, but it be interesting to understand. There is an interesting relation with statistical physics, of course, and over the last year there have been 3 papers computing properties, of compressed sensing problems using the replica method. This approach gives an alternative and much more constructive and concrete way of getting the same results and more results. Okay, that's basically it. Thank you.
Questions for Andrea?
What's the connection with Bregman? Bregman, you mean successive projections on
Right,
convex sets. So
right.
what are the 2 convex sets?
Yeah. So if you Bregman for convex optimization means
It's successive projection, right, to get at an intersection.
Well, it's not exactly that. There is a more general version for convex optimization, but yes, it's similar. You project on the constraint and then you minimize, etc. But okay, so the connection is, I don't know what is, the brief answer is that I don't know really what is the connection, except that if you look at Bregman, okay, the iteration looks very similar, but it's not quite the same. So they have something very similar to this kind of recursion with this kind of term here, except that this term is not quite the same, and the coefficient, they don't quite know how to fix them. Okay, so here what I discussed is a completely different point at arriving at this, and of course we get a somewhat different final algorithm.
So you're thinking of the Onsager term as collapsing a step where you're projecting onto
Right.
some other convex set.
Right.
So
Yeah.
What is the corresponding meaning of the Onsager terms in physics? What do you call it Onsager terms?
Okay, so this is related, if you were in Balaji's talk yesterday, there is this idea of, so this dates back to the 50s, right? This idea of, I want to understand the behavior of particle in a complex material, so I pull out of particle. So the simplest thing is, okay, what physicists call mean field. I'll treat the outside material as something that affects my particle, and then I write a fixed point just as a medium that affects my particle, and then I write a fixed point equation for this medium. The particle must behave as the medium. Okay, so the observation of Onsager was that okay, you have to keep into account, that when you take out the particle, the medium is not quite the same because you created a hole. So there is the medium with the hole that you can take into effect. Okay? In other words, you have to take into effect the reaction of this particle on the rest. Okay? So in some cases, like these cases, this appears to be really relevant. Right? So there is a whole long story of many models in which since then this has been precised. Okay? This is one chapter of this story.
The sparsity assumption in compressed sensing comes from the observation in practice. A lot of data has a lot of zeros
Right.
in certain bases, right? But what about the random A assumption in your model? Does it make sense in practice? Is there motivation from practice?
Right. So the completely random, I don't think it's really practical because it's very difficult to implement an instrument that has IAD random measurement entries. But for instance, the random Fourier section, this has a lot of meaning in practice, right? It corresponds to I'm taking Fourier coefficients of my signal, but I'm not taking all of them. I'm not taking the full, but only a random subset of them, right? So this is, or similar things you might think that hold in practice, right? Now, at the moment, we don't know how to prove anything about the Fourier case, but all the theory seems, all the empirical evidence says that there is not a lot of difference between the random and the non-random, right?
But then the ultimate goal would be to actually design these matrices, right? That's like the coding theory problem.
Right. But it's like since you bring up the coding theory topic, right? You start by designing random codes, right? And you have a lot of ways to do theory for random codes. Then you construct structure codes, and in the end, the best structure codes actually behave like random codes, right? So.
Yeah, but that's justified by Shannon's information capacity result, right? So you have to have an analogous result here to show that.
Yeah, but okay. But the point that I'm making is just that when you actually go about constructing codes, good codes, good structural codes, the more the better they are, the closer they are indeed to random, right? In a number of ways. So, and for instance, in algorithmic ways, right?
No, but what I'm saying is that the random codes is optimal was justified by Shannon's capacity theorem.
Sure.
But there is no analogous theorem here, right?
But the random matrix stuff was here.
No. What he did was he analyzed the performance of random matrix A. But suppose I can design A, he did not say that you cannot get better performance.
Right. This doesn't exist. I mean, the folklore theorem here is that somehow you cannot get better than this. And the analogous of the Shannon would be this line in the delta rho plane.
Right.
And of course, this is not an information theoretic line, because if you just try to get information theoretic bounds, first of all, you know the distribution, and then you can get much better, right? So, for specific matrices, you can prove upper bounds, right? Matrix ensemble. So there are two elements. There is the matrix ensemble and the thing.
In practice, how easy is it to perform the algorithm? I mean, you need an optimization, right, at every step.
No, I don't need any.
To get the coefficients.
Which coefficients?
The B or theta or whatever you call it.
Theta is predicted by the theory somehow. So all of these results, we computed theta. Theta is in reality, in these results, theta is the current variance of the current estimate times a single number. And this single number I can compute in advance. I have a closed form expression for it. It's just a function of the sparsity. Okay? So this you don't really have to optimize over. So it's really, apart from this coefficient that you have to read up in a table, there is really no overhead on this iterative soft thresholding.
If you did not insist on reconstructing all the coefficients exactly, would you recover the line at 1 or?
No. Okay. So what does it mean? No reconstruct. Then where is the line, right? So which line do you want? I mean, of course, if you say I want to reconstruct with whatever error, you get the line at 1, right?
But you want exact reconstruction. If you allow small fractions of errors.
Okay, so here, so if you see how the error behaves above this line, here it departs continuously. So here it's about linear function of rho minus rho critical. So it goes up linearly and then goes monotonically up to 1, right? Another question is what happens if there is a little bit of noise. Now you cannot reconstruct in any point correctly. So let's say that you have the problem I started from, that was y equals a s naught plus w naught, and this has variance equal b. Okay, now you compute the mean square error at the end, okay, at the end of the algorithm. So below the line, the mean square error is about a coefficient that depends on delta and rho times v. Okay, so in this regime, the error at the end is just the same order as the noise, modulo a coefficient. In other words, even if I'm undersampling a lot, the error doesn't blow up. Okay, so this is a bounded coefficient. Okay, so this coefficient blows up as you get at the line. So this means that in this region, all this thing is stable with respect to noise, and the reason above is not stable with respect to.
Okay. Oh, one more question.
Your main theorem is with respect to Gaussian matrix. How would you compare this type of theory, the results, where if you took it like conditional Gaussian estimation, but now it's an L2?
Conditional Gaussian estimation of the vector, I mean
of S not given Y.
Of S not given Y overall, you never reconstruct it exactly, right?
Right, you never, yeah.
Okay.
But how does this compare? Because here you're trying to go for an L1 reconstruction.
Right. So how does it compare, with respect to which metric?
L2.
Okay. So I think that you will not obtain this behavior, right? This is really, so this will be, here it's proportional to B, right? So let's say that you are noise. So here this is something that is pretty amazing, that I'm undersampling, and still I'm not increasing the noise in my estimate, right? So the L2 norm is the same as the noise in my measurements, okay? If I do linear estimation, well, this will be of order 1, okay? So there is, the ratio is arbitrarily large. Right? Now, if you look at it in absolute terms, depends on the point of the plane where you are. If you are in a corner, it will be pretty good, but this is really a qualitative difference, right?
Okay, so let's take a break, and we'll resume at 11 o'clock.
Consume and then